Start with a silent, breathtaking shot of a vast, orange desert under a pale, white sun. The landscape is alien, with immense, wind-scoured rock formations and dunes of red-black sand. The sky is a thin, hazy violet. The only sound is a low, mournful whisper of wind. The year is 1 billion A.D. This is not Mars. This is not some distant exoplanet in an unfamiliar star system. This world is our home. Or rather, it was. This is planet Earth. The great blue oceans that once defined this world are gone, boiled away into a thick, suffocating atmosphere. The verdant continents, once teeming with life, have been scoured clean by unrelenting heat and sterilized by radiation. The air itself is a toxic brew, unbreathable, a crushing blanket of carbon dioxide and steam. The sun, once a nurturing yellow star, now hangs in the sky as a bloated, overly brilliant white orb, nearly 10% more luminous than in our time. It is a furnace door left ajar. There are no cities, no ruins, not even the fossilized memory of bone. 1 billion years is an eternity, an expanse of time so profound that it erodes not just mountains and monuments, but the very chemical signatures of a civilization. In this profound, terrible silence, one question echoes louder than any sound. Where are we? After 1 billion years of cosmic evolution, stellar mechanics, and the relentless march of time, what became of humanity? Did the brilliant, quarrelsome, star-gazing ape that once dominated this world simply fade away? Or did we, against all odds, find a way to endure, to transform, to carry the flickering candle of consciousness out into the great, star-dusted dark? Our story is not yet finished. But its final chapters will be written on a canvas of time so vast it challenges our very ability to comprehend. To understand the chasm of 1 billion years, we must first recalibrate our sense of time. Imagine the entire 13.8 billion year history of the universe compressed into a single calendar year. The Big Bang happens in the first second of January 1st. Our own Milky Way galaxy doesn't fully form until May. Our solar system, our sun, our Earth, are latecomers, coalescing from dust and gas in early September. The first complex, multicellular life on this planet, the Cambrian explosion, doesn't occur until the middle of December. The dinosaurs, those magnificent rulers of a lost world, roam the Earth from Christmas Day until they are abruptly wiped out on December 30th. And humanity? All of our recorded history, from the first Sumerian clay tablets to the missions to Mars, occupies only the last 10 seconds before midnight on New Year's Eve. The Roman Empire rises and falls in less than a second. The Renaissance is a flicker. Your entire lifetime is a nearly imperceptible sliver of the final tick of the clock. The question we are asking is what happens to our species by next April, in the calendar of the cosmos. It is a journey into the deep future, a future governed by forces of unimaginable power and scale. The first and most inexorable of these forces is the loyalty of our own star. Our sun has been the engine of life on Earth for over 4 billion years. It is a predictable, stable, middle-aged star, a sphere of incandescent plasma powered by the most fundamental process in the universe, nuclear fusion. Deep within its core, pressures and temperatures beyond any earthly comparison crush hydrogen atoms together to form helium. Each second, 600 million tons of hydrogen are converted, releasing a torrent of energy that radiates outwards, warming our world and fueling all life. But this process, this benevolent stellar heartbeat, has a built-in clock of obsolescence. The sun is not a perpetual motion machine. It is a star with a finite lifespan, and it is aging. As the hydrogen in the sun's core is fused into helium, this helium ash builds up. It is denser than the surrounding hydrogen and sinks to the very center, forming an inert core that does not participate in fusion. This growing helium core exerts a powerful gravitational pull, squeezing the surrounding shell of hydrogen, increasing the pressure and temperature. This, in turn, accelerates the rate of nuclear fusion in that shell. It's a feedback loop. The consequence is subtle yet apocalyptic. The sun is slowly, relentlessly getting brighter. For every billion years that pass, our star's total energy output increases by roughly 10%. This is the great, silent threat that looms over our distant future. A gentle warming that will, over geological time, become a planetary execution. The process has already begun. A billion years from now, that 10% increase in luminosity will be the fatal blow. Long before that, however, the Earth will begin to feel the strain. In perhaps 200 million years, the initial effects will become undeniable. The planet's thermostat, a delicate dance of carbon dioxide cycles and rock weathering, will begin to fail. The tropics, humanity's ancestral home, could become lethally hot for months at a time, forcing migrations on a scale we cannot imagine. The planet will grow feverish. By 600 million years from now, we reach a catastrophic tipping point. The increasing solar energy will accelerate the evaporation of water from the oceans. Water vapor is a potent greenhouse gas, far more effective at trapping heat than carbon dioxide. More heat leads to more evaporation, which leads to more water vapor in the atmosphere, which traps even more heat. This is the moist greenhouse effect, a runaway cycle of planetary warming from which there is no return. The atmosphere will become thick with steam, and the temperature will begin to spiral upwards. The oceans, the cradle of all life on this world, will begin to boil. Picture it, a slow, inexorable steaming. First the shallow coastal waters, then the great abyssal plains. The surface of the planet becomes a global sauna, with pressures and temperatures that would kill any complex life instantly. The sky, once blue, would be perpetually shrouded in a thick, white haze of cloud and steam. Life's great chemical engine, photosynthesis, will grind to a halt. The elevated temperatures will destroy the complex proteins that plants use to capture sunlight. The great forests and phytoplankton blooms will wither and die, starving the atmosphere of new oxygen. The planetary life support system will shut down, one component at a time. Any life that survives will be microbial, extremophiles clinging to existence in cooler, subterranean pockets, a final, faint echo of Earth's once glorious biosphere. By the 1 billion year mark, the process is complete. The Sun, now a visibly larger and harsher star in the sky, has baked our world into sterility. The oceans have vanished, their water dissociated by solar radiation into hydrogen and oxygen. The light hydrogen escapes into space, lost forever. The Earth is dry, hot, dead. A world more akin to modern-day Venus than the lush Eden we know. This is our planet's default trajectory. The fate written in the laws of stellar physics, discovered by pioneering astrophysicists like Arthur Eddington in the early 20th century. They peered into the hearts of stars using the language of mathematics and revealed not only how they shine, but also how they must inevitably die, and in doing so, how they will one day destroy their own children. For any version of humanity to survive this future, it cannot be on Earth. Our species must leave the cradle permanently. But the Sun is not the only cosmic threat we face. Our galaxy, the Milky Way, is a beautiful, sprawling metropolis of 400 billion stars. But like any metropolis, it is not without its dangers. It is a dynamic, and sometimes violent, place. Lurking throughout its spiral arms are ticking time bombs, massive stars, dozens of times heavier than our Sun, that live fast and die young. At the end of their lives, they collapse under their own immense gravity and explode with unimaginable fury. We call these explosions supernovae. A single supernova can briefly outshine its entire host galaxy. It unleashes a flood of high-energy radiation and particles that can sterilize anything in its immediate cosmic neighborhood. Fortunately, the odds of a star going supernova close enough to cause us direct, catastrophic harm within 50 light-years or so are exceedingly low. But there is a more sinister and far more potent variant of stellar death, a gamma-ray burst, or GRB. These are the most powerful explosions the universe has witnessed since the Big Bang itself. Imagine a hypermassive, rapidly spinning star collapsing into a black hole As material falls into the nascent black hole, immense jets of energy, focused by powerful magnetic fields, are blasted out from its poles. These are not explosions that radiate in all directions. They are focused beams of gamma rays, traveling at the speed of light. They are cosmic death rays, capable of traversing thousands of light years with their lethal power intact. If such a beam were to strike the Earth, even from halfway across the galaxy, the consequences would be devastating. The burst itself would last only a few seconds, but its impact would be felt for decades. The immense flood of gamma rays would slam into our upper atmosphere, ripping apart nitrogen and oxygen molecules. This would trigger a cascade of chemical reactions, creating vast quantities of nitrogen oxides. These compounds would rapidly destroy the ozone layer, our planet's fragile shield against the sun's ultraviolet radiation. With the ozone layer gone, the full, unfiltered harshness of solar UV rays would pour down, scorching the surface of the planet. It would be lethal to most life on land and in the upper layers of the ocean, triggering a mass extinction event on a global scale. Some paleontologists speculate that just such an event, a distant GRB, may have been the culprit behind the Ordovician extinction 450 million years ago, which wiped out 85% of all marine species. Over 1 billion years, the odds of Earth taking a hit from a GRB are not zero. It is a game of cosmic roulette, and we have no way of knowing when the gun is pointed in our direction. The galaxy holds other, slower, but equally potent threats. Our solar system is not an isolated island. It is in constant motion, orbiting the galactic center once every 230 million years. During this grand cosmic journey, we drift through denser and more sparsely populated regions of the galaxy. Occasionally, we will pass relatively close to other stars. A direct collision is fantastically unlikely. Space is simply too big, but a close encounter is a certainty. A passing star doesn't need to hit us to wreak havoc. It only needs to pass through the Oort cloud. The Oort cloud is a vast, theoretical sphere of trillions of icy comets surrounding our solar system, extending almost a light year out into space. It is the outermost remnant of the primordial disk from which the planets formed. Most of these comets are in stable, distant orbits, posing no threat. But the gravitational nudge from a passing star would be like kicking a colossal hornet's nest. It would disrupt these stable orbits, sending a shower of comets hurtling into the inner solar system. Not one or two, but potentially millions of them. For thousands, perhaps millions of years, Earth and the other inner planets would be subjected to a relentless bombardment. The age of impacts that ended the dinosaurs would seem trivial by comparison. The sky would be filled with new, bright comets, a beautiful and terrifying sight, each one a potential world killer. Humanity's continued existence would depend on a planetary defense system of unparalleled sophistication and endurance. And then there is the largest scale event of all, a galactic merger. Our nearest major galactic neighbor, the Andromeda Galaxy, is currently 2.5 million light-years away, but it is not staying there. It is hurtling towards our Milky Way at a speed of over 250,000 miles per hour. In roughly 4.5 billion years, the two galaxies will collide and begin a long, majestic, and violent process of merging into a single, giant elliptical galaxy, which some have nicknamed Milkomeda. While 1 billion years from now we will only be in the early stages of this approach, the gravitational effects will begin to be felt. The great, graceful spiral arms of both galaxies will be torn asunder by tidal forces. Vast streams of stars will be flung out into intergalactic space. The rate of star formation will skyrocket as immense clouds of gas and dust are compressed, leading to a burst of new, massive, and short-lived stars, and thus more supernovae. Our solar system itself could be thrown into a completely different orbit, possibly much closer to the new, chaotic galactic core, a region filled with intense radiation and a supermassive black hole. The night sky of our distant descendants would be an unimaginable spectacle, a canvas of fire and creation, but the environment could be far more hostile than the quiet galactic suburb we currently inhabit. These are the threats from without, the uncaring machinations of the cosmos. But humanity also faces dangers born from our own planet and from within ourselves. The ground beneath our feet feels solid, but it is a thin, brittle crust floating on a sea of molten rock. The Earth is a living, breathing planet, and sometimes it breathes fire. We are familiar with volcanoes, but deep beneath the surface lie threats of a completely different order of magnitude: supervolcanoes. Places like Yellowstone in North America or Lake Toba in Indonesia are not mountains with a crater at the top. They are vast, collapsed underground chambers or calderas, dozens of miles wide, brimming with magma. When one of these erupts, it does not produce a lava flow, it produces an explosion that can alter the course of civilization. An eruption of the Yellowstone supervolcano would be thousands of times more powerful than Mount St. Helens. It would blast 1 trillion tons of ash, rock, and gas into the atmosphere. A thick blanket of ash would cover half the North American continent, burying cities, destroying agriculture, and poisoning water sources. But the global effects would be even worse. The immense cloud of sulfur dioxide injected into the stratosphere would encircle the globe, reflecting sunlight back into space. This would trigger a volcanic winter, a sudden and dramatic drop in global temperatures that could last for a decade or more. Growing seasons would fail worldwide, global food chains would collapse, famine and conflict would be inevitable. Humanity has faced this before. The eruption of the Toba supervolcano 74,000 years ago was so colossal that some scientists believe it pushed our ancient ancestors to the very brink of extinction, reducing the entire human population to perhaps only a few thousand individuals. Over 1 billion years, multiple super eruptions are not just possible, they are a statistical certainty. Each one would be a test of our resilience, a filter through which our species must pass. Yet, perhaps the most profound challenge is not eruption or impact, but the slow, inevitable pressure of evolution itself. The history of life on Earth is a story of constant change and replacement. 99.9% of all species that have ever lived are now extinct. Extinction is the rule, not the exception. Survival is the anomaly. From the perspective of deep time, Homo sapiens times is a fleeting phenomenon, a single twig on the immense, sprawling tree of life. Why should we be any different? Even if our lineage persists, would our descendants 1 billion years from now still be human? The answer is almost certainly no. 1 billion years is an unimaginable stretch of evolutionary time. Consider that it has only been about 6 million years since our lineage diverged from that of chimpanzees. Look at the profound changes that have occurred in that relatively short span. Bipedalism, tool use, complex language, civilization. Now, project that rate of change forward not by 6 million, but by 1 times billion times years. The beings that exist then, even if they are our direct descendants, might be as different from us as we are from the first simple bacteria. Evolution could take them in any number of directions, dictated by the environments they inhabit. If humanity remains on a single world, it could speciate, diverging into multiple distinct forms, adapted to different niches, much like Darwin's finches. But if, as survival dictates, humanity spreads to the stars, the evolutionary pressure would be immense and varied. Descendants living on a high-gravity world might evolve to be shorter, stockier, with denser bones. Those living in the low-gravity environment of Mars or a space habitat might become taller, more gracile, their bodies slowly losing the adaptations for Earth's pull. In the cold, dark outer solar system, colonists might need to genetically engineer themselves to withstand radiation or metabolize different chemicals. Over 100 million years, these separate populations could become so biologically different that they would be considered entirely new species. Unable to interbreed, the very concept of humanity as a single, unified species would cease to exist. We would be the common ancestor, a distant, primitive memory to a dazzling and diverse array of post-human species scattered across the galaxy. This isn't extinction in the traditional sense, but a form of evolutionary transcendence. We would survive, but not as us. The greatest challenge of all, however, may not come from the stars or the Earth, but from our own clever hands. Our species is defined by its technology. We have learned to split the atom, to rewrite the genetic code, to create artificial intelligence. These tools give us unprecedented power to shape our destiny, but they also represent existential risks of our own making. A genetically engineered pandemic, far more lethal and contagious than anything nature could produce, could be unleashed by accident or by malice. A runaway artificial superintelligence, with goals misaligned with our own, could view humanity as an obstacle or an irrelevance. Our own tribal, short-sighted nature, which has served us well for millennia, could lead to catastrophic wars fought with weapons of unimaginable destructive power. In a sense, the next few centuries represent the Great Filter, a concept that tries to explain why we see no evidence of other intelligent life in the cosmos. Perhaps every technological civilization reaches a point where its power to destroy itself far outstrips its wisdom to control that power. Passing through this filter and surviving our own technological adolescence is the most immediate and critical test humanity will ever face. So, the outlook seems bleak. A dying sun, a dangerous galaxy, a volatile planet, and our own self-destructive tendencies. Is there any hope? Yes. Because the same ingenuity that creates existential risk also creates the possibility of salvation. If we are to have a future a billion years from now, it will be because we used our intelligence to overcome the limitations of our birth world and our biology. The first and most crucial step is to become a multiplanetary species. Spreading to another world is the ultimate insurance policy against any single event that could wipe us out on Earth, be it an asteroid, a supervolcano, or a self-inflicted catastrophe. The obvious first candidate is Mars, but transforming Mars from a cold, dead world into a second Earth is a project of staggering scale and complexity, likely to take centuries, if not millennia. Imagine the task. It is akin to attempting to perform planetary CPR on a world that has been frozen and clinically dead for 3 billion years. First, we would need to warm it. This would involve generating immense quantities of greenhouse gases, perhaps by building massive factories that pump fluorocarbons into the thin air, or by steering carbon-rich asteroids to crash into the surface. The goal would be to trigger a deliberate, controlled, runaway greenhouse effect, the very process that will destroy Earth, but which could resurrect Mars. As the planet warms, the carbon dioxide frozen in the polar ice caps, and the soil would sublimate, thickening the atmosphere. With a thicker atmosphere, liquid water could exist on the surface once more. The great Martian canyons could once again fill with rushing rivers. A shallow northern ocean could reform. Then would come the biological phase, seeding the new seas with genetically engineered microbes and algae designed to survive the harsh Martian environment and begin producing oxygen. For hundreds of years, the planet would be a construction site, a canvas for planetary engineering. Eventually, our descendants could walk on the surface of a blue, green, and red Mars under a thicker, warmer sky without a spacesuit. It would be a monumental achievement the moment humanity truly shed its terrestrial skin. But Mars is only a temporary reprieve. It, too, will be sterilized by the expanding sun just a few 100 million years after Earth. To truly secure a long-term future, we must venture further out into the realm of the gas giants. Here, worlds like Jupiter's moon Europa or Saturn's moons Titan and Enceladus offer tantalizing possibilities. These are not places we could terraform in the traditional sense. They are ice worlds, or worlds shrouded in a thick nitrogen haze. Survival there would require a radical redefinition of what it means to be human. On Europa, with its vast subsurface ocean kept liquid by Jupiter's tidal forces, our descendants might live in submersible cities, harvesting geothermal energy from hydrothermal vents on the ocean floor. They might engineer themselves to withstand the crushing pressures and the cold, perhaps even incorporating bioluminescence. On Titan, with its liquid methane lakes and rivers under a thick orange sky, they might build domed habitats and develop a completely different kind of biochemistry. These would be new cradles for new kinds of humanity, scattered seeds taking root in alien soil. Ultimately, however, even the solar system is a temporary home. To survive for 1 billion years, to outlast our own sun, our lineage must take the greatest step of all. We must go interstellar. The challenge is almost beyond words. The distances are a form of tyranny. The nearest star to our sun, Proxima Centauri, is over 4 light-years away. Our fastest current spacecraft, the Voyager probes, would take over 70,000 years to cover that distance. To cross the void between stars in a reasonable time frame requires a fundamental revolution in propulsion technology. Perhaps we will harness the power of nuclear fusion, creating miniature stars within our engines to drive ships at a significant fraction of the speed of light. Or maybe we will build vast, gossamer-thin solar sails pushed by the light of the sun, or even more powerfully, by colossal laser arrays based on Earth or the Moon. This is the idea behind projects like Breakthrough Starshot, which envisions sending tiny, wafer-thin nanocraft to the nearest stars, accelerated to 20% of the speed of light by a gigawatt laser beam. These would be robotic explorers, but the same principle could one day be scaled up for larger vessels. For journeys to more distant stars, even these speeds may not be enough. This leads to the concept of the generation ship, a self-contained world in a bottle. A massive ark, kilometers long, carrying a community of thousands on a journey that will last for centuries or even millennia. They would have to be completely self-sufficient, recycling every atom of air, water, and waste. They would need a stable ecosystem, a robust social structure, and a profound sense of purpose to survive the immense psychological strain of their eternal voyage. The generations born aboard these ships would never know a planet. The ship would be their only world. The stars outside their windows would be their only landscape. They might forget their origins, their mission becoming a form of religion. When they finally arrived at their destination, 1,000 years later, would their culture and even their biology still be recognizably human? And then there are the dreams of science fiction, the hopes that we might one day cheat the tyranny of distance by discovering new physics. Could we learn to warp space-time, as proposed in the Alcubierre drive, creating a bubble of reality that allows for faster-than-light travel without breaking Einstein's laws? Could we find or create wormholes, tunnels through space-time that connect distant points in the cosmos? These ideas remain purely theoretical, mathematical curiosities. But if they, or something like them, ever prove possible, they would transform humanity into a truly galactic species, able to traverse the stellar gulfs as we now cross oceans. But what if the ultimate form of survival involves abandoning the biological form altogether? This is the trajectory of post-humanism, a future where we merge with our technology so completely that the distinction ceases to exist. The process could begin with genetic engineering and cybernetics. We could design our children to be immune to disease, to have enhanced intelligence, to be able to withstand the vacuum of space or the radiation of a distant star. We could replace our fragile, organic limbs with more durable and powerful mechanical ones. We could integrate our brains directly with computers, granting us instant access to all of humanity's knowledge. We would become a new species, Homo technologicus, masters of our own evolution. The final step in this journey would be to shed the body entirely, mind uploading. The idea is to scan a human brain, neuron by neuron, synapse by synapse, and create a perfect digital replica of a consciousness. This digital mind could then live inside a vast supercomputer, a virtual reality of its own choosing. Freed from the constraints of biology, from aging, disease, and death, a digital consciousness could live for billions of years. It could experience countless lifetimes in intricate, simulated worlds. It could travel across the galaxy at the speed of light as a simple information stream, beamed from one star system to another, downloaded into a robotic body or another computer upon arrival. Humanity could become a civilization of pure information, living within colossal computational structures like matryoshka brains, concentric spheres built around a star to capture all of its energy output for computation. This would be a form of immortality, a way for consciousness to survive until the very end of the universe itself. But it raises the most profound philosophical question of all. Is a copy of a mind the same as the original? Is that digital ghost in the machine still you? Is that survival? Or is it merely leaving a very sophisticated echo behind? We return, finally, to where we began, to the silent, scorched surface of Earth 1 billion years from now. The sun glares down on a world devoid of memory. The grand experiment of terrestrial life is over. The silence here presents two starkly different possibilities for the fate of humanity. The first is a silence of absence. It is the possibility that we failed, that we were a brief, beautiful, but ultimately doomed species. Perhaps we succumbed to the filter of our own technology, wiping ourselves out in a flash of nuclear fire or a silent, engineered plague. Perhaps we never managed to leave Earth in a meaningful way, and were slowly, inevitably, cooked by our aging star. In this scenario, all our art, our science, our love, and our wars were for nothing. Just a momentary, localized flicker of complexity in an indifferent universe. Our legacy is this silent rock, our only epitaph the whisper of the sterile wind. The universe did not notice our passing, but there is a second possibility. The silence on Earth might not be one of absence, but of transcendence. It might be the silence of an empty nest. In this future, we succeeded. We saw the threats coming and acted. We had the wisdom, the courage, and the foresight to overcome our tribalism and work together as a species. We navigated the treacherous shoals of our technological adolescence and emerged as mature, responsible custodians of our own destiny. We left our home world not as panicked refugees, but as graceful explorers. In this scenario, humanity still exists, just not here. Our descendants, in 1,000 different forms we can barely imagine, thrive among 1,000,000 stars. Some may be biological, adapted to strange new worlds with alien skies. Others may be beings of pure energy and light, vast digital intellects exploring the fundamental nature of reality itself. They may have forgotten the name Earth, or remember it only as a sacred, mythical place of origin, but they carry within them the unbroken chain of consciousness that began in the ancient savannas of Africa. The spark survived. The question, will humanity still exist in 1 billion years, is not truly a question about the future. It is a question about the present. It is a mirror held up to our species, reflecting our greatest fears and our most profound hopes. Our long-term survival depends not on some future technology yet to be invented, but on the choices we make today, on our ability to manage our planet, to cooperate with each other, to invest in science and exploration, and to think in terms of geological timescales. The journey of 1 billion years begins with a single step. The cosmos, in all its terrible beauty and infinite possibility, is waiting to see which path we choose. For a single, fleeting moment, everything you have ever known is here. The rust-red deserts of Mars etched by the ghosts of ancient water. The colossal swirling fury of Jupiter's great red spot, a storm wider than our entire world, raging silently in the cold vacuum for centuries we cannot count. You are adrift in a sea of familiar lights, the celestial neighbourhood we call home. But we are not stopping here. We are leaving the gentle glow of our sun behind. Past the icy rings of Saturn, a celestial jewel box of frozen dust and rock. Beyond the lonely tilted axis of Uranus and the deep blue mystery of Neptune, we are pushing past the final whispers of our star's influence into the great silent darkness between the suns. The scale begins to shift your human perspective, dissolving like salt in an ocean. Stars that were once individual pinpricks of light now blur into vast shimmering clouds. You are plunging through the Orion Nebula, a stellar nursery, where gas and dust under the patient, relentless crush of gravity are collapsing to ignite new suns, birthing solar systems yet to be. It is a cosmic cathedral of creation, painted in hues of hydrogen pink and oxygen blue, a masterpiece sculpted by shockwaves from dying giants and the fierce radiation of newborn titans. The distances become staggering, the numbers losing all meaning. Light years, once an abstract measure, are now the meters on our journey's odometer, and we are just getting started. The camera of your mind continues to pull back faster now, accelerating beyond comprehension. Our entire galaxy, the Milky Way, with its 400 billion suns, its central supermassive black hole, a sleeping monster, its spiral arms, a glittering pinwheel of cosmic dust and stellar fire, shrinks to become a single swirl of light in the darkness. It is our island, our home, beautiful and impossibly vast. And yet it is only one. Out here in the intergalactic void you can see other islands, Andromeda, our sister galaxy, hurtling towards us on a collision course set for 4 billion years from now. The Triangulum Galaxy, a smaller companion bound with us in a gravitational dance. Together we are part of a small cluster of galaxies, the local group. But even this feels provincial, a tiny cosmic village. So we pull back further still. Our local group becomes an insignificant speck lost in a river of galaxies, a supercluster containing 100,000 more, all drawn together by a gravitational anomaly. We have named the Great Attractor, a destination we can feel but cannot see. This is the Laniakea supercluster, our home on the grandest of scales, a web of galactic filaments stretching across 500 million light-years. And still we continue our impossible retreat. The intricate web-like structure of the universe reveals itself. Filaments of galaxies separated by voids of near-perfect emptiness, a cosmic tapestry woven from dark matter, and luminous stars stretching in every direction. Look, every point of a light you now see is not a star, not a solar system, but an entire galaxy, each with its own hundreds of billions of suns, its own countless worlds, its own potential for life, its own unique story unfolding over cosmic timescales. 2 trillion galaxies. That is our best estimate for the observable universe. 2 trillion islands of light scattered across 93 billion light-years of expanding space. This is the known cosmos, the grand, breathtaking and utterly humbling arena of our existence. And now we have reached the edge. Not an edge made of rock or wall, but an edge made of time. Before you is a faint mottled glow, a wall of ancient light permeating all of space. This is the cosmic microwave background radiation, the afterglow of creation. It is the oldest light in the universe, a snapshot of the moment 380,000 years after the beginning, when the cosmos cooled just enough for light to finally travel freely. It is the echo of the Big Bang. For decades, this was our ultimate horizon, the baby picture of our universe, the first page of the cosmic story we thought we knew. We believed that by looking at this wall of light, we were staring at the absolute beginning of everything. The singular, explosive moment that created all of space, all of time, all of matter. The one unique event that birthed our reality. This grand, majestic 2 trillion galaxy-strong universe. This was it. The whole story. But what if it isn't? What if this entire magnificent structure, all of it, is nothing more than a single bubble in a pot of boiling water? What if the cosmic afterglow we see is not the wall at the end of the museum, but merely the wall of our own tiny room? What if our Big Bang was not the beginning, but just a beginning? This is the precipice of a revolution in our understanding of reality, a conceptual leap so profound it threatens to shatter our very definition of the word universe. It is born from a theory that was first designed to solve problems with our own Big Bang story, a theory called cosmic inflation. To grasp its power, we must first rewind the clock, go back past the galaxies, past the first stars, past that wall of ancient light. Back to the very first fraction of the very first second of time. Here in this primordial state, the universe was unimaginably hot and dense, a roiling soup of fundamental particles and energy. The conventional Big Bang model tells us that from this point space simply began to expand and cool like the embers of a cosmic fire. But this simple picture left nagging questions. Why is the universe so uniform on the larger scales, as if distant regions which never had time to communicate somehow agreed on the same temperature? Why is the geometry of our universe so perfectly flat balanced on a knife edge between collapsing and flying apart forever? Our universe appeared to be fine-tuned, a cosmic coincidence of impossible precision. Cosmologists needed a mechanism, something that happened before the Big Bang we knew, to set the stage so perfectly? The answer they found was breathtaking in its violence and its elegance: inflation. In the first sliver of a second, a moment so small it makes a nanosecond look like an eternity, a strange form of energy with a powerful anti-gravitational force is thought to have seized control. This was not a gentle expansion. This was a hyper-acceleration and exponential and utterly ferocious stretching of the fabric of reality itself. During this period, a patch of space smaller than a proton was stretched to a size larger than the entire observable universe is today. It was the ultimate growth spurt, an event that took the microscopic quantum world and magnified it to cosmological proportions. This incredible stretching flattened the geometry of space, just as inflating a crumpled balloon smooths out its wrinkles. It took a tiny uniform patch and expanded it so vastly that it would appear uniform everywhere, solving the great puzzles of our cosmic architecture. Inflation was the secret architect, the silent partner to the Big Bang. It was the event that primed the pump that loaded the dice that made our universe possible. At the end of this inflationary epoch, that strange energy decayed, dumping its enormous potential into a firestorm of particles and radiation. This moment of decay, this reheating of the cosmos, is what we have traditionally called the Big Bang. It wasn't an explosion in space. It was the moment the inflationary stretching stopped and the more leisurely expansion we see today began. For a time, this was a satisfying addition to our cosmic story. Inflation was the preface to the book of our universe. But then the physicists who created the theory, men like Alan Guth and Andre Linde, realized something astonishing, something their own equations were screaming at them. What if the inflation once started never fully stopped? This is the genesis of the theory of eternal inflation. It posits that inflation is not a historical event that happened once and then ended. Instead, inflation is the eternal default state of the cosmos. It is a process that is always happening somewhere. Imagine not a single inflating balloon, but an infinite bubbling foam, a vast ocean of inflating space driven by that same mysterious anti-gravitational energy. This is the metaverse, the true cosmic backdrop. Within this eternally inflating ocean, quantum fluctuations are constantly at play. By pure chance, in some random pockets of this foam, the inflationary energy can fluctuate downwards. It can decay just as it did for us. In that tiny patch, the hyper-acceleration grinds to a halt. The energy is released, a fire is lit, a big bang occurs, and a new bubble universe like our own is born. This new universe begins to expand and cool according to its own laws. It is self-contained, an island of stability in the chaotic inflating sea. It has its own stars, its own galaxies, its own cosmic microwave background. And to any observer living inside that bubble, their afterglow, their cosmic horizon, would seem like the absolute edge of everything, the one and only beginning. They would be blissfully unaware of the violent creative process raging just outside their space-time. Because while this bubble universe has been born, the ocean around it has not stopped inflating. In the time it took for that one patch to decay, the space between it and other regions has expanded by an incomprehensible amount, isolating the new universe forever. And in that ever-expanding ocean, new quantum fluctuations are happening. More patches decay, more Big Bangs ignite, more bubble universes spring into existence. It is a chain reaction that has no end. An infinite cosmic fractal where each universe is just one branch on an eternally growing tree. Our universe, with its 2 trillion galaxies and its 93 billion light-year span, is rendered a single grain of sand on an infinite beach. Our Big Bang, the event we once held as the ultimate origin, is demoted to a local affair, a commonplace cosmic event, one of countless trillions happening over and over again. The implications are almost too vast for the human mind to contain. If this model is correct, then out there beyond our cosmic horizon, beyond the reach of our most powerful telescopes, lies an infinity of other worlds, other cosmoses born from the same eternal engine. These universes might not look like ours. The quantum fluctuation that ended inflation in their patch could have been different, leading to different amounts of dark energy, different fundamental particles, perhaps even different laws of physics. Some universes might be stillborn, collapsing back on themselves in an instant. Others might be barren empty voids where stars could never form, but in an infinite sample, everything that can happen will happen. There would be universes with physical constants so finely tuned for complexity that they make our own look mundane. Universes with different dimensions of space and time. Universes so utterly alien they defy our capacity for imagination. And somewhere scattered among this infinite variety, there would be universes almost identical to ours, where a different choice you made this morning branched off into a new reality. This isn't just a wild story. It is the logical and, for many physicists, the unavoidable consequence of the theory of inflation. Our best explanation for the structure of the cosmos we see around us. It suggests that the ultimate reality is not a single lonely universe, but a magnificent ever-birthing multiverse. The Big Bang. Our beginning is not a unique miracle. It is a process that may still be happening right now somewhere else. But this raises the most profound question of all. If we are trapped inside our own bubble forever causally disconnected from these other worlds, how could we ever know? Is this staggering vision forever confined to the realm of mathematics and metaphysics? Or is it possible that the birth of our own universe left a clue, a faint primordial scar imprinted on the very fabric of our reality? A cosmic echo from a collision with another bubble long ago. The search for that evidence is now one of the most exciting frontiers in all of science. A quest to find the first tangible proof that we are not alone in the cosmos in the most fundamental way imaginable. A quest to see beyond our own beginning. What if the entire history of our universe, every star, every galaxy, every life form is merely a single fleeting sentence in an infinite cosmic story that is still being written? For generations we believed we had found the opening chapter to that story, a moment of creation so powerful it set the stage for everything we know. It's a narrative etched into the very fabric of space-time, a tale of a singular explosive beginning from an unimaginable point of infinite density. We call it the Big Bang. And for decades it has stood as one of science's most triumphant achievements, a theory so robust, so predictive, it seemed to answer the ultimate question of our origins. The evidence is not buried in ancient texts, but woven into the light of the cosmos itself. If you could build a radio telescope sensitive enough and point it toward the empty spaces between the stars, you would hear it. A persistent, faint, inescapable hum, a whisper from every direction at once. This is the cosmic microwave background, the fossilized echo of creation. Discovered almost by accident, this ghostly afterglow is the universe's first light released, when the cosmos was a mere 380,000 years old. It's the radiation from the dying embers of the primordial fireball stretched by cosmic expansion over 13.8 billion years from a searing gamma-ray glare into the cold, gentle microwaves we detect today. When our satellites like Planck and WMAP mapped this ancient light, they revealed a stunning portrait of the infant universe. An almost perfectly uniform glow, a testament to a time when everything was crushed together in a hot, dense, unified state. This wasn't just a lucky guess. It was a direct prediction of the Big Bang model, a confirmed message from the dawn of time. But the theory offered more than just a picture. It provided a recipe. In the first few minutes after the beginning, the universe was a nuclear furnace of unimaginable temperatures and pressures. It was a place too hot for atoms to exist, a seething soup of fundamental particles. Here in this crucible of creation, the very first elements were forged in a process called Big Bang nuclear synthesis. As the universe expanded and cooled with breathtaking speed, protons and neutrons fused together, creating the building blocks of matter. The Big Bang model doesn't just suggest this happened, it makes a precise, falsifiable prediction. It dictates the exact proportions of these primordial elements, roughly 75% hydrogen, 25% helium, and a tiny trace amount of lithium. When we point our telescopes to the most ancient pristine gas clouds in the distant cosmos, clouds untouched by the alchemy of stars, we find exactly those proportions. The cosmic cookbook written in the first 3 minutes of time matches observation with breathtaking fidelity. These pillars of evidence, the expansion of space discovered by Hubble, the afterglow of creation, and the precise elemental abundances came together to form a magnificent, coherent story. A story of a universe born from a single point, expanding and cooling with gravity, slowly gathering the primordial matter into the first stars and then into the vast, glittering spiral galaxies that fill our skies. It was a complete, elegant, and powerfully validated narrative. It felt like we had finally understood the grand architecture of existence. Yet as our understanding deepened, as our questions became more precise, we began to see unsettling cracks in this beautiful foundation. For all its successes, the standard Big Bang model, when scrutinized, presented us with paradoxes so profound they threatened to bring the entire structure crashing down. The story, it turned out, was missing its very first page. The first great mystery is one of sublime, impossible uniformity. We call it the horizon problem. The cosmic microwave background radiation, the echo of the early universe, is almost the exact same temperature in every direction we look. To one part in 100,000, the temperature is identical, whether we look toward the constellation Orion or in the completely opposite direction toward Libra. On the surface, this uniformity seems logical. If the universe started as a hot, dense soup, it makes sense that it would have an even temperature. But there's a fatal flaw in that logic, a flaw rooted in the ultimate speed limit of the cosmos, the speed of light. Imagine two ancient regions of space, one on the far left of our observable universe and one on the far right. Today they are separated by over 90 billion light years. But when that first light was released, they were already separated by millions of light years. Since nothing can travel faster than light and the universe was only a few 100,000 years old, there was simply not enough time for any signal, any heat, any information to have travelled between them. They were outside each other's causal horizon. They could not have possibly communicated. They had no way to know about each other, no way to exchange energy and settle on a common temperature. It's like finding two people on opposite sides of the Earth who have never met or spoken spontaneously, deciding to wear the exact same outfit down to the last thread. It makes no sense. The uniformity we observe, the very smoothness that seems so natural, is a flagrant violation of the laws of physics as we understood them. The Big Bang model offered no explanation for this cosmic conspiracy. It simply demanded that we accept it as a bizarre, inexplicable initial condition. The universe, for some unknown reason, just started out this way, perfectly coordinated across distances that should have been forever isolated. This wasn't an explanation. It was an admission of defeat, a deep puzzle that pointed to a fundamental misunderstanding of our cosmic origins. The second problem is even more precarious, a challenge of cosmic architecture we call the flatness problem. In the grand scheme of things, space-time itself has a geometry. According to Einstein's theory of general relativity, the shape of the universe is determined by a cosmic tug-of-war between the outward momentum of its expansion and the inward pull of gravity from all the matter and energy within it. There are three possibilities for its ultimate shape. It could be closed, like the surface of a sphere with so much matter that gravity would eventually halt the expansion and cause it to collapse in a big crunch. It could be open, like the surface of a saddle, with too little matter for gravity to ever stop its runaway expansion, causing it to grow cold and empty forever. Or it could be perfectly flat, balanced on a knife's edge between these two fates. A flat universe would expand forever, but the rate of expansion would continuously slow, approaching zero. All of our measurements, from the cosmic microwave background to the distribution of distant galaxies, indicate that we live in a universe that is almost perfectly, uncannily flat. The total density of matter and energy in our cosmos is staggeringly close to the critical density required for this perfect balance, and here lies the problem. The state of perfect flatness is a profoundly unstable equilibrium. Think of balancing a pencil on its sharpened point. The slightest nudge, the tiniest deviation, and it will immediately fall over. For the universe, any tiny deviation from perfect flatness, in the first moments of the Big Bang, would have been amplified exponentially over 13.8 billion years of expansion. If the initial density had been just a tiny fraction higher, the universe would have collapsed back on itself billions of years ago. If it had been a tiny fraction lower, it would have expanded so rapidly that galaxies and stars would never have had a chance to form. For our universe to be as flat as it is today, its density at 1 second after the Big Bang had to be fine-tuned to the critical value to an accuracy of 1 part in a quadrillion. At the earlier, more extreme moments in time, the precision required is even more absurd, bordering on the supernatural. It's a fine-tuning so exquisite it defies all logic. The standard Big Bang model offers no reason for this cosmic balancing act. It just posits that the universe began with this miraculous, infinitely precise setting, another unexplained initial condition that feels less like a scientific theory and more like a lucky roll of the cosmic dice. Why was our universe born walking this impossibly thin gravitational tightrope? The theory was silent. The third and final paradox emerges from the fiery intersection of cosmology and the strange world of particle physics. It is the riddle of the missing monsters, the monopole problem. Our most successful theories of fundamental particles suggest that in the extreme heat of the very early universe, the distinct forces of nature we see today, electromagnetism, and the weak and strong nuclear forces were unified into a single symmetric superforce. As the universe expanded and cooled, it underwent a series of phase transitions, much like steam condensing into water and then freezing into ice. During these transitions, the fundamental forces froze out and separated, breaking the initial symmetry and becoming the distinct forces we now observe. This process is a cornerstone of modern physics, but it comes with a disturbing prediction. Just as defects like cracks or crystal dislocations can form when water freezes into ice, these cosmic phase transitions should have created massive stable topological defects in the fabric of space-time. The most notable of these are called magnetic monopoles, fundamental particles that are like an isolated north or south pole of a magnet, something never seen in nature. According to the theories, these monopoles should have been created in colossal numbers during the early universe. They would be incredibly massive, stable, and ubiquitous. The universe should be absolutely teeming with them. In fact, the theories predicted so many that their collective gravity would vastly outweigh all the stars and galaxies combined. Their gravitational pull would have been so immense that it would have immediately halted cosmic expansion and caused the universe to recollapse into a singularity when it was just a few thousand years old. But when we look out into the cosmos, we see nothing. Our most sensitive detectors have never conclusively found a single magnetic monopole. Their complete absence is a deafening silence, a direct and startling contradiction between the predictions of our best particle physics and the observed reality of our universe. It was a cosmic crime scene with no body, and the standard Big Bang model was the prime suspect, unable to account for the missing evidence. Three profound, seemingly unrelated crises, the impossible smoothness, the miraculous flatness, and the missing monsters had brought cosmology to a standstill. The triumphant theory of the Big Bang was shown to be not a complete story, but a beautiful narrative with a critically flawed beginning. A new idea was needed, something revolutionary, something that could explain not just how the universe evolved, but why it was born with such bizarrely perfect and improbable properties. The answer would come not from a grand observational discovery, but from a moment of pure theoretical insight, a flash of inspiration in the mind of a young particle physicist named Alan Guth in 1979. While wrestling with the monopole problem, Guth stumbled upon a radical mechanism that he soon realized could solve all three cosmological puzzles in one elegant stroke. He called it inflation. The idea was as simple as it was audacious. What if in the very first fraction of a second after its birth, before the familiar, more sedate expansion of the Big Bang took hold, the universe underwent a brief but ferocious period of exponential superluminal growth? It wasn't just an expansion, it was a detonation of space itself. A moment of hyper-expansion driven by the energy of a strange quantum field, where the universe doubled in size and then doubled again and again, at least 100 times overall, in less than a trillionth of a second. In this infinitesimal sliver of time, a patch of space smaller than a single proton was stretched into a volume vastly larger than our entire observable universe today. This wasn't a minor tweak to the Big Bang model. It was a new, violent and spectacular prequel. And its consequences were profound. Suddenly the horizon problem vanished. Before inflation began, the region of space that would become our entire observable cosmos was a minuscule subatomic domain. It was so tiny that it was easily in causal contact, allowing it to reach a state of perfect thermal equilibrium. Every part was connected to every other part, smoothing out any temperature differences. Then inflation took this tiny uniform patch and magnified it to astronomical proportions. The reason we see the same temperature in every direction is because we are looking at a vastly inflated piece of what was once a single, smooth, causally connected neighbourhood. The impossible coordination was no longer impossible. The flatness problem was solved just as elegantly. Inflation acts like a cosmic steamroller, flattening the curvature of space-time. Imagine an ant living on the surface of a tiny crumpled balloon. To the ant, the curves, bumps and folds are obvious. But now inflate that balloon to the size of the Earth. From the ant's perspective, its local patch of the surface would appear perfectly undeniably flat. Inflation does precisely this to the geometry of the universe. It expands space so violently and on such a colossal scale that any initial curvature, no matter how dramatic, is stretched out to near perfect flatness. The universe doesn't have to be born on a gravitational knife's edge. Inflation forces it there. This incredible fine-tuning is no longer a miraculous coincidence, but an inevitable physical consequence of that first explosive moment. And what of the missing monsters, the magnetic monopoles inflation provided the perfect cosmic hiding place? The monopoles were indeed created just as particle physics predicted in the fiery moments before inflation began, but then the hyper-expansion of space kicked in. The same process that stretched the universe to an enormous size also diluted the density of these massive particles to near zero. It's like putting a single drop of ink in a small glass of water, and then suddenly expanding that glass to the size of an ocean. The ink is still there, but it is spread so thin as to be effectively gone. Inflation scattered the monopoles so far and wide that the chance of finding even one in our entire observable universe is practically non-existent. They weren't missing. They were simply banished to the unimaginable voids beyond our cosmic horizon. With one powerful, stunningly simple idea, the great paradoxes that had plagued cosmology for a decade were resolved. Cosmic inflation didn't replace the Big Bang. It saved it, providing the essential opening act that set the stage for everything that followed. It explained the unexplainable, transforming a series of improbable coincidences into the predictable outcome of fundamental physics. It was a theoretical revolution, a new vision of our origins that was beautiful, compelling and powerful. But this dramatic solution brought with it a new, even more mind-bending question. The quantum field that powered this incredible burst of creation, the inflaton field, did its work and then decayed, releasing its energy to create the matter and radiation of the hot Big Bang. But what if somewhere out there in the infinite expanse beyond our view it didn't stop? What if the explosive engine of creation, having ignited once, never truly turned off? And so the picture of our cosmic dawn seemed nearly complete, a breathtaking but fragile theory of unimaginable beginnings. We had our mechanism inflation, a phenomenal burst of expansion, driven by a mysterious energy field, the inflaton. This process could explain the universe's baffling flatness, its uniform temperature, and the very seeds of galaxies. It was a triumph of human intellect, a story that fit the evidence. But every great story has its ending, and inflation's conclusion was a profound and unsettling puzzle. How did the universe apply the brakes? How did it transition from that state of exponential fury into the more sedate cooling expansion we see today? This was the so-called graceful exit problem, a loose thread that when pulled threatened to unravel everything. The very mechanism that made inflation so powerful, its self-sustaining nature also made it incredibly difficult to shut down. For the universe to become the home we know, filled with stars and life, inflation had to end, and it had to end everywhere more or less at once. Or so it was thought. The quest for that ending led physicists down a rabbit hole deeper and more fantastic than any of them had anticipated. In the early 1980s, the intellectual atmosphere was electric. At the Lebedev Physical Institute in Moscow, a young theorist named Andrei Linde was wrestling with the equations that governed this primordial state. Across the world at Tufts University, Alexander Vilenkin, another brilliant mind, was exploring the same treacherous theoretical landscape. They weren't trying to create a multiverse, they were simply trying to be rigorous. They were trying to make inflation work to tie up that loose end. They focused their attention on the very heart of the process, the quantum nature of the inflaton field itself. We imagine it as a smooth, uniform sea of energy, but at the quantum level nothing is ever truly still. There is always a jitter, a fundamental uncertainty, a constant hum of particles winking in and out of existence. This is the restless quantum foam that underlies all of reality, a ceaseless microscopic tremor in the fabric of space-time. During inflation, these tiny quantum fluctuations in the inflaton field were stretched to colossal astronomical scales, becoming the subtle variations in density that would one day grow into galaxies. This was the source of everything we see. And for a time, it also seemed to be the perfect solution to the exit problem. Imagine the inflaton field as a vast high-altitude plateau, a grand upland of cosmic potential. Inflation is the process of this field slowly, gently rolling downhill from this high-energy plateau towards a low-energy valley. As long as it remains on the plateau, the universe expands exponentially. When it finally drops into the valley, its energy is released in a colossal burst of heat and matter. The event we call the Big Bang's fireball, and inflation in that region gracefully comes to a halt. The quantum fluctuations were the key. They ensured that the field wasn't rolling downhill perfectly smoothly. Instead, it was a jittery, uncertain descent. In some places, a random quantum fluctuation might give the field a little nudge, hastening its fall into the valley below. In others, the roll might be slightly slower. This quantum randomness was supposed to be the the cosmic signal that told inflation its time was up. It was the mechanism for the graceful exit. But here, buried deep within the mathematics, Linda Vilenkin and others began to uncover a staggering reality-altering paradox. They were staring at a mathematical snake eating its own tail. The very quantum fluctuations that could nudge the inflaton field downhill ending inflation in one patch of space had an equal and often much greater probability of doing the opposite. A random upward quantum leap could kick the field back up the plateau, pushing it away from the valley and reinforcing the inflationary state. Consider the sheer violence of the expansion. During every tiny fraction of a second, the inflating space was doubling in size, then doubling again and again on a timescale almost too small to comprehend. This expansion was so powerful, so overwhelmingly dominant, that it could take a tiny region where a quantum fluctuation had kicked the inflaton uphill and explode it to a volume far greater than all the regions where inflation was ending. The process wasn't just continuing, it was actively breeding. The parts of space that kept inflating were growing so much faster than the parts that stopped, that on average the total volume of inflating space was always increasing, and in fact, increasing exponentially. This was the point of no return for our cosmic worldview. The graceful exit, the idea of a single universal end to inflation, dissolved into a statistical impossibility. Linda's calculations showed something utterly profound. Inflation, once it begins, might never fully stop. Not everywhere. Not ever. The process becomes eternal. It's not an event that happened in our past. It is a physical process that is likely still happening right now, on scales far beyond our cosmic horizon. The Big Bang wasn't a singular moment of creation for the entire cosmos. It was simply the moment inflation ended here. This revolutionary concept, known as eternal inflation, paints a picture of reality that dwarfs every cosmology that came before it. Imagine a vast churning ocean of inflating space-time, the raw, untamed substrate of reality itself. This is the metaverse, the eternally expanding canvas. Within this furious ocean, quantum fluctuations are constantly at play, like the unpredictable frothing of waves. In most of this ocean, the expansion continues unabated, the space-time stretching and growing at a blistering pace. But every so often, in a random localized pocket, a quantum fluctuation conspires to roll the inflaton field down into its valley. In that tiny spot, the spell is broken. Inflation stops. The stored energy of the inflaton field is unleashed, creating a hot, dense fireball of matter and radiation. A universe is born. This newborn reality, this bubble of space-time, begins its own journey of slower expansion and cooling, completely unaware of the raging tempest from which it emerged. It is an island of relative calm and order in an endless sea of chaotic expansion. But the ocean itself doesn't care. It keeps inflating. And as it expands, it creates yet more room for yet more quantum fluctuations to randomly trigger the end of inflation in other disconnected locations. Another bubble universe nucleates, and another, and another. Each one a self-contained cosmos expanding into the inflating superspace around it. They are like bubbles forming in a pot of boiling water, or perhaps more accurately like raisins in an endlessly growing loaf of dough. Each bubble is a complete universe, potentially infinite in its own right, with its own Big Bang, its own history, its own destiny. Our observable universe, everything we have ever seen or could ever hope to see from our own planet to the most distant galaxy, is just one of those bubbles. Our entire cosmic history from the Big Bang 13.8 billion years ago until now is merely the local story of what happened inside a single, successful bubble in a cosmic foam of countless others. The implications are almost too vast for the human mind to contain. It means the Big Bang was not the beginning, but a beginning. A local event in a timeless, eternal, and self-reproducing cosmos. This isn't merely philosophical speculation. It emerged as an unavoidable consequence of combining our best theories of cosmology and quantum mechanics. André Linde developed what he called chaotic inflation, showing that even under very general starting conditions, inflation would naturally become an eternal self-perpetuating process. There was no need for fine-tuning or special circumstances. Once you have an inflaton field with the right properties, eternal inflation isn't just possible, it's practically inevitable. The multiverse is not an addition to the theory, it is the theory's most startling prediction. This shatters our place in the cosmos, in a way not seen since Copernicus displaced the Earth from the centre of the solar system. We are not just on a typical planet orbiting a typical star in a typical galaxy. We may be living in a typical universe, one of a potentially infinite number of universes that have been budding off from the eternal engine of inflation for all of time. This grander structure, this multiverse, has no beginning and no end. It is a fractal-like process constantly creating new cosmic domains. The parent spacetime continues to inflate, giving birth to daughter universes, which themselves are isolated, unable to communicate with one another, because the inflating space between them is expanding faster than the speed of light. We are in this view the inhabitants of a single isolated cosmic oasis. The light from other bubble universes will almost certainly never reach us. Their existence is forever beyond our direct observation, hidden by the insurmountable barrier of the inflating sea that separates us. We are fundamentally cut off adrift in our own pocket of reality. This raises a deep and troubling question for the nature of science itself. If we can never see these other worlds, if we can never receive a signal from them, is the multiverse a scientific theory at all? Or is it a beautiful mathematical story that must forever remain in the realm of metaphysics? For many, this was a bridge too far. The idea of unseeable, untestable realities felt like a betrayal of the scientific method. Science, after all, is built on observation evidence and falsifiability. How can you falsify a theory whose primary prediction is the existence of things we can never ever touch or measure? The debate ignited a firestorm in the cosmological community, a deep philosophical divide that persists to this day. Is eternal inflation the ultimate expression of our cosmological models, the logical endpoint of our quest to understand origins? Or is it a sign that our theories have gone astray, leading us away from testable physics and into a landscape of pure imagination, and yet the mathematics remains stubbornly persuasive? The models that so beautifully explain the universe we can see seem to point inexorably to the existence of universes we cannot. To abandon eternal inflation would mean finding a flaw in the fundamental marriage of quantum mechanics and general relativity as they apply to the earliest moments of time. It would require some new unknown physics to intervene, a cosmic governor that somehow forces inflation to stop everywhere, at once violating the very quantum principles that give the theory its power. So far, no such mechanism has been found. Instead of a flaw, physicists like Vilenkin began to see it as a guide. If our universe is just one of many, perhaps its properties are not absolute. Perhaps they are, in a sense, environmental accidents. The specific way the inflaton field finally decayed in our bubble determined the particular particles and forces that would populate our cosmos. A different decay in a different bubble could result in a universe with a completely different set of physical laws. A universe with stronger gravity, or with only 2 forces instead of 4. A universe without electrons, or where light moves at a different speed. Most of these universes would likely be sterile, unstable flashes in the cosmic pan, incapable of forming complex structures like stars, let alone life. But with an infinite number of bubbles being created, the seemingly impossible becomes the statistically inevitable. By sheer chance, some bubbles like ours would happen to have the precise combination of physical laws and constants that are hospitable to the formation of complexity and ultimately consciousness. We find ourselves in a universe that appears exquisitely fine-tuned for our existence, for the simple reason that we could not exist to ask the question in any of the other more common sterile universes. The multiverse, once seen as a bug in the theory of inflation, was now being recast as its most profound feature. It offered a potential explanation for one of the deepest mysteries in all of science, why our universe seems so perfectly, so improbably suited for life. We are left standing at the edge of a conceptual precipice. Behind us lies the comfortable notion of a single unique cosmos, our entire reality, contained within one grand sweeping story. Before us lies an infinite foam of possibilities, a reality so vast and so strange that our own universe is reduced to a single grain of sand on an endless shore. The theory of eternal inflation doesn't just expand our map of space and time, it forces us to redefine what the word universe even means. It suggests that the ultimate reality is not a static stage, but a dynamic, self-reproducing machine for making new worlds. But if we are truly sealed within our own cosmic bubble, is there any hope of ever finding proof? Is there any conceivable scar, any echo or remnant from this violent birth process that might have been imprinted upon our own universe at its inception? Perhaps the creation of our bubble wasn't a perfectly clean break. Perhaps in the distant past our infant universe collided with another bubble, another nascent reality expanding nearby in the metaverse. Such a collision would be the most cataclysmic event imaginable, a shockwave propagating across the entire sky. And it just might have left a subtle lasting bruise on the oldest light in our universe, a faint pattern we could one day hope to detect. And so, we arrive at a precipice of understanding, a cognitive ledge, where the very logic of our most successful theory of creation pushes us toward an idea so staggering, so utterly transformative, that it threatens to shatter our every conception of reality. The quantum jitter, that inherent uncertainty we found at the heart of the inflaton field, was not merely a curious footnote in the story of our own beginning. It was not a problem to be solved or an anomaly to be explained away. Instead, it was a signpost, a cryptic message encoded in the mathematics pointing toward a conclusion as inescapable as it is profound. It was the key that would unlock the final, terrifying and magnificent implication of the inflationary paradigm. Think back to that primordial sea of energy, the false vacuum stretched taut and humming with unimaginable potential. Inflation, this engine of cosmic expansion, was driven by its quantum state. And here is the crucial step, the pivot upon which our entire cosmic view now turns quantum mechanics, is a game of chance, not a predictable machine of cause and effect. For any given patch of that inflating ocean, there was only a probability that the inflatant field would roll down its potential hill and decay, ending its reign of hyper-expansion and birthing a universe. In our corner of this inflating cosmos, the dice landed in our favour. The field cascaded downwards, its energy transforming in a fiery exhalation that became the quarks, the leptons, the photons, the very substance of our world. This was our Big Bang, the moment our own cosmic clock started ticking. But what about the regions next to us and the regions next to them? In the strange calculus of the quantum world, if something can happen, it eventually will happen. And if it has a probability of not happening, then somewhere it won't. So while our local patch of the inflaton field decayed, countless other patches, by the sheer blind luck of quantum probability, did not. They remained in that high-energy false vacuum state. And what does a false vacuum do? It inflates. It continues to stretch space-time at that exponential, incomprehensible rate, doubling in size every fraction of a second. This is the genesis of the theory of eternal inflation. It is not an addition to the original idea, not an exotic embellishment. It is the theory's own logical destination. The very mechanism that made our universe flat, smooth and vast carries within it the seeds of its own immortality. The process once started may never truly end. Imagine a vast seething cauldron of boiling liquid representing the inflating cosmos. Our universe is like a single bubble that suddenly formed within that liquid, a region where the water cooled and turned to steam, expanding rapidly. Inside that bubble, a new reality takes hold with its own matter and its own destiny. But outside our bubble, the rest of the liquid remains at a roaring boil, and it is expanding far faster than our own bubble can grow. The boiling liquid, this parent spacetime, is creating new volume at a rate that utterly dwarfs the expansion of the universe within our bubble. And because it continues to boil, new bubbles are forming within it constantly. Each bubble is a new universe, a new Big Bang event. Each one is born from a quantum fluctuation that allows a local patch of the inflaton field to finally decay, releasing its stored energy into a furnace of new particles. These pocket universes, these newborn bubbles of space-time, are propelled away from each other by the still inflating sea that separates them. The space between the bubbles grows so astonishingly fast that they become causally disconnected from one another almost instantly. No light, no signal, no information could ever cross the inflating chasm that separates one pocket universe from another. They are forever adrift cosmic islands in an eternal sea of creation, each one utterly oblivious to the existence of the others. This is the multiverse, not a fanciful speculation from science fiction, but the seemingly unavoidable outcome of our best theory for our own origin. Our universe ceases to be the universe. It becomes a single, perhaps unremarkable member of an infinite cosmic foam, a glittering, self-reproducing architecture of reality, where Big Bangs are not a singular, unrepeatable miracle, but a routine, ongoing process of cosmic reproduction. This vision requires a complete and humbling recalibration of our place in existence. That singular flash of creation we have revered for a century as the ultimate beginning, our Genesis moment is demoted. It becomes just one local event, one spark in an endless fireworks display. The true stage is not our universe, but the eternally inflating superstructure that spawns it. The real story is not the story of a single bang, but of an endless fractal-like budding of new realities. Picture a magnificent, impossibly large tree growing in an endless void. The trunk represents the initial onset of inflation, but as it grows, it branches. Each branch is a vast region of inflating space-time, and from those branches, smaller branches sprout, and from those still more. Every so often on one of these countless branches, a leaf unfurls. That leaf is a pocket universe. That leaf is us. Its delicate network of veins represents our galaxies and superclusters, but the tree itself continues to grow, sprouting new branches and new leaves forever and ever. The tree is the multiverse, and its growth is eternal inflation. Our entire observable cosmos, every star you have ever seen or imagined, every galaxy the Hubble telescope has ever photographed, all of it, would be less than a single atom on the surface of one of those leaves. This perspective is as philosophically shattering as it is scientifically elegant. It suggests that the beginning of our time was not the beginning of all time. Our origin story, the narrative we have pieced together from the cosmic microwave background, is merely a local parish record in a library that contains an infinity of volumes, each telling the tale of a different cosmic birth. The laws of physics themselves, which we have long pursued as universal and absolute truths, may be nothing more than local bylaws, parochial regulations, that solidified in our particular corner of the multiverse when the inflaton field decayed here. The way the field decayed, the specific energy state it settled into, could have determined the fundamental constants of nature. The strength of gravity, the speed of light, the mass of the electron, these values that we hold so sacred that make our existence possible, might be entirely arbitrary. They are the result of a cosmic roll of the dice. In another pocket universe born from a different quantum fluctuation, the inflaton field might have decayed in a completely different way, settling into a different vacuum energy state. In that universe, the strong nuclear force might be a little weaker, preventing stars from ever igniting. That universe would be a dark, cold, sterile expanse of hydrogen gas forever. In another, gravity might be much stronger, causing it to collapse back on itself a microsecond after its birth, a failed creation, a cosmic miscarriage. In yet another, the cosmological constant could be so powerfully repulsive that it rips apart every atom before a single galaxy has a chance to form. The multiverse then is not just an infinite collection of universes like our own. It is a vast experimental laboratory, a landscape of possibilities where every conceivable set of physical laws might be realized somewhere. Most of those universes would be stillborn, hostile to complexity, devoid of the delicate balance required for structure, let alone for life. They would be evolutionary dead ends in the cosmic ecosystem. From this vantage point, our universe is revealed for what it might be: a stunningly rare and fortunate accident. We find ourselves in a universe with laws of physics that are exquisitely fine-tuned for our existence, for the simple reason that we could not have evolved in any of the others. We exist because we exist. This is the anthropic principle, an idea that has long made physicists uncomfortable, as it can feel like a circular argument, a scientific surrender. But within the framework of eternal inflation, it finds a natural and powerful home. It's no longer a mystery why our universe is so perfectly suited for life, any more than it is a mystery why we find ourselves living on a planet with liquid water and a breathable atmosphere. We're here because this is one of the few places in the vast cosmic expanse where the conditions are right for beings like us to emerge and ask the question. We won the cosmic lottery. The prize was not just a planet or a solar system or a galaxy. The prize was an entire universe complete with a bespoke set of physical laws that allowed for the miracle of chemistry, biology, and consciousness. This framework also elegantly resolves some of the deepest lingering puzzles about our own cosmos. Why did the cosmological constant, the energy of empty space, have the tiny non-zero value that we measure today? A value so small that it seems absurdly fine-tuned, differing from theoretical predictions by an astronomical 120 orders of magnitude. In the multiverse, there is no single value. There is a near-infinite spectrum of values across all the pocket universes. Some are huge and positive, ripping their universes apart. Some are huge and negative, crushing them in an instant. And a very, very small number by pure chance will have a value close to zero, like the one we observe. Only in those universes can galaxies form and observers evolve. Our universe's most baffling fine-tuning problem might be nothing more than a selection effect. We are simply living in one of the universes where it was possible to live. The implications ripple outwards, touching everything we thought we knew. The concept of eternity itself is transformed. Our universe is fated to end perhaps in a heat death of cold, dark emptiness, or a dramatic big rip where space-time itself is torn asunder. But the multiverse, the engine of eternal inflation, may have no end. It may also have had no beginning. Some models suggest that the inflating sea has always existed, a timeless eternal substrate from which universes are perpetually born. Our Big Bang was not the ultimate origin point, but just an event in a process that has been unfolding and will continue to unfold forever. We are the brief, flickering consciousness of one temporary bubble in an ocean that is truly eternal. It is a humbling, almost terrifying thought, reducing our grand cosmic drama to a local play on a provincial stage. But it is also an idea of breathtaking scope and grandeur. It suggests that the universe is fundamentally, irrepressibly creative, that the act of creation is not a one-time event, but an ongoing, unending property of the cosmos itself. We are forced to confront the limits of our perception, the boundaries of what we can ever hope to know. This cosmic foam, this infinite tapestry of worlds, lies forever beyond our reach. The relentless expansion of the parent space-time that separates the bubbles ensures that we are and always will be prisoners of our own universe. We can never visit these other worlds. We can never receive a signal from them. We can never see them even with the most powerful telescope imaginable. They are outside our observable horizon and forever will be. Their existence is written not in the stars we can see, but in the very logic of the theories that describe our own cosmic dawn. They are ghosts in the machine's silent siblings whose presence we can infer but never directly confirm. And this leads us to the most profound and difficult question of all, a question that strikes at the very heart of the scientific enterprise. If we can never see, touch, or measure this multiverse, is it truly science? Or have we, in our relentless quest to understand our origins, pushed ourselves beyond the boundaries of testable physics and into the realm of pure metaphysics? How do we grapple with a theory that posits an infinite, unseeable reality as the explanation for our own existence? It is a challenge that has divided the world of physics, pitting some of its greatest minds against each other in a battle over the soul of their discipline. The grand vision of eternal inflation born from the quantum whispers of our own creation has given us a breathtaking picture of our place in the cosmos. But it has also led us to the edge of an epistemological abyss, forcing us to ask, what does it mean to truly know something? And so we find ourselves cast adrift in an ocean of infinities. The grand sweeping tapestry of eternal inflation, once a mere mathematical curiosity, now presents us with a reality so vast, so utterly overwhelming, it threatens to capsize the very ship of science we used to navigate here. What does it mean to exist within one bubble universe, when an eternally frothing sea of others expands beyond any conceivable horizon? Each a self-contained cosmos, each potentially governed by its own unique set of physical laws. This is no longer just a question of cosmology. It is a question that strikes at the heart of what we can ever hope to know. For centuries, the power of physics has resided in its predictive certainty. You give it a set of initial conditions and it tells you with astonishing precision what will happen next. It predicts the arc of a thrown stone, the orbit of a distant planet, the energy released by a dying star. Prediction is the engine of science, the mechanism that separates a powerful theory from a beautiful but empty guess. But the multiverse born from eternal inflation presents us with a profound, perhaps even fatal paradox. In a cosmos where literally anything that can happen will happen. An infinite number of times over, what does it mean to predict anything at all? This is the abyss that physicists call the measure problem, and it represents one of the most severe intellectual crises in modern theoretical physics. Imagine trying to calculate the average height of a person. A simple task, you might think. You would gather a representative sample of people, measure them, and compute the average. But now imagine trying to do that if there were an infinite number of people. The very concept of an average collapses into meaninglessness. No matter how many people you measured, you would have only sampled an infinitesimally small fraction of the total. Any answer you got would be completely dependent on how you chose to count on the specific method you used to sample an endless population. This is precisely the dilemma we face in the cosmic multiverse. We are trying to ask simple questions. What is the most common value for the cosmological constant? What kind of universe is most likely to form? To answer, we need to be able to take a cosmic census to count the bubble universes and sort them by their properties. But how do you count to infinity? How do you define a typical universe when the sample size is eternal? The act of counting, of measuring the multiverse, is not a passive observation, but an active choice, and every choice of how to count gives a wildly different answer. Think of it as trying to map an infinite city that is perpetually building itself. One physicist might decide to count universes based on their volume. This seems intuitive. Bigger, older universes should count for more. But this volume measure leads to a bizarre prediction. It suggests that the vast majority of universes are ancient, cold and empty, having long since undergone their heat death. By this measure, our own hot, young, vibrant universe is so impossibly rare that our existence becomes a near zero probability event. This cannot be right. A theory that predicts we shouldn't exist is not a very useful theory. Another physicist might suggest a different approach. Perhaps we should count observers, not just volumes of space. This makes some sense. We should focus on the places where life could arise. But this too leads to a labyrinth of paradoxes. Consider the strange case of the Boltzmann brains. In an eternally fluctuating cosmos over unimaginable timescales, it is statistically possible for atoms to randomly assemble themselves just for a fleeting moment into a fully formed conscious brain, complete with false memories of a life it never lived. Some calculations suggest that in an infinite multiverse, these spontaneously generated disembodied observers would vastly, overwhelmingly outnumber observers like us who evolved over billions of years on a stable planet. If this measure is correct, you should be concluding right now that you are not real. You are a momentary flicker of organized matter in the void, a statistical fluke whose universe is an illusion. Again, we are led into a philosophical dead end, a conclusion that defies our most basic experience of reality. This is the dizzying vertigo induced by the measure problem. Every attempt to impose a natural way of counting, of taming the infinite productivity of eternal inflation, seems to fail. The proper time measure, the causal patch measure, the stationary measure, each is a brilliant, intricate attempt by some of the world's greatest minds to create a kind of cosmic ledger, a way to make sense of an infinite inventory. and each one so far has led to predictions that seem to contradict what we see, or worse, descend into absurdity. Without a solution, eternal inflation is not a single theory, but an infinity of theories masquerading as one. It becomes a framework that predicts everything, and in doing so perhaps predicts nothing at all. The grandest vision of modern cosmology hangs in the balance tethered to a question we don't yet know how to ask, let alone answer. How do we give meaning to infinity? And yet this very crisis of meaning might hold the key to one of the oldest and most profound questions we have ever posed. Why are we here? Not in the spiritual sense, but in the cold, hard, physical sense. Why does our universe possess the exquisitely specific set of properties that allows for the existence of stars, planets, chemistry, and ultimately us? This is the great puzzle of cosmic fine-tuning. For decades, we have known that our existence seems to depend on a series of astonishing cosmic coincidences. If the force of gravity were just a fraction of a percent stronger, stars would have burned out far too quickly for life to evolve. If it were slightly weaker galaxies and stars might never have formed at all. Change the mass of the neutron by a tiny amount and the delicate nuclear reactions that forge the elements of life inside stellar furnaces would break down. Tweak the value of the cosmological constant, that strange dark energy pushing our universe apart, and the consequences are catastrophic. A little more and its repulsive force would have ripped the cosmos apart before galaxies could ever coalesce. A little less and gravity would have won, collapsing the universe back on itself long before the first stirrings of life. The value we observe is so bizarrely small, so precisely dialed in, it's like finding a single pencil, balanced on its point across the entire observable universe. It is a universe walking a tightrope. The constants of nature appear to be tuned with breathtaking precision for the emergence of complexity and life. For a long time, this was a deeply uncomfortable fact for physics. It felt arbitrary. It smelled of something beyond science. Some saw in this precision the hand of a divine creator, an intelligent designer who set the cosmic dials just right. Others simply threw up their hands, accepting it as a brute fact, the way the world just happens to be with no deeper explanation required. But eternal inflation offers a third revolutionary possibility, one that is both deeply humbling and scientifically audacious. It suggests there is no mystery at all. This potential solution is called the anthropic principle. In the context of the multiverse, it is devastatingly simple. If there are infinite bubble universes and the laws of physics, the strengths of forces, the masses of particles vary randomly from one bubble to the next, then it is no surprise that we find ourselves in one of the rare universes where the conditions are right for life. We couldn't possibly find ourselves anywhere else. It's like asking why you find yourself living on Earth, rather than on the scorching surface of Mercury, or in the frozen clouds of Neptune. You're on Earth because it is one of the few places in our solar system where beings like you can live. The observation itself creates a powerful selection bias. The multiverse transforms the fine-tuning problem from a miracle into a statistical inevitability. Imagine a cosmic casino with an infinite number of slot machines, each one pulling the levers to set the physical constants for a new universe. Almost all of them come up with losing combinations universes that are empty, sterile, or fleetingly brief. They might be filled with nothing but radiation or collapse into a black hole a microsecond after they are born. But if you play an infinite number of times, eventually by pure chance one machine is going to hit the jackpot. It will produce that one perfect life-sustaining combination of laws. The anthropic principle simply states that we are the winners of that cosmic lottery, looking back and marvelling at our own good luck. We shouldn't be surprised we won, because only the winners are around to ask the question in the first place. This is a profound shift in our cosmic perspective. It suggests that the laws of nature in our universe are not fundamental and universal, but are merely local bylaws, environmental accidents. The speed of light, the charge of an electron, the strength of gravity. These numbers that we have long revered as the bedrock of reality might be no more fundamental than the number of planets in our solar system or the atmospheric pressure at sea level on Earth. They are simply the values that happen to freeze out from the chaos of inflation in our particular cosmic patch. Our universe is not the universe, it is just universe, one of an infinite variety of possibilities realized in some unimaginably vast and hidden cosmic landscape. For many scientists, this is a beautifully elegant explanation. It takes a seemingly supernatural problem, the fine-tuning of the cosmos, and solves it with the natural machinery of eternal inflation. It removes the need for a designer or for inexplicable brute facts. The universe isn't fine-tuned for us. We are simply living in one of the universes that happens to be fine-tuned. The Copernican revolution, which dislodged Earth from the centre of the solar system, is now extended to its ultimate conclusion. Not only is our planet not special, and our star not special, but our entire universe and its sacred physical laws may not be special either. We are just one ordinary outcome of an extraordinary process. But for a growing number of physicists and philosophers, this explanation feels deeply unsatisfying, even dangerous for science itself. The anthropic principle in this multiverse context is accused of being a surrender, a retreat from the search for deeper understanding. The goal of physics has always been to explain why things are the way they are, to find the unique, necessary and elegant equations that could not be any other way. The multiverse, however, tells us there is no deeper reason. The constants are what they are in our universe simply because in other universes they are different. This is not an explanation, critics argue, but an abdication of the need to explain. It's like asking an engineer why a bridge is designed a certain way and being told, because in an infinite multiverse all possible bridge designs exist and this is just one of them. You haven't learned anything about the principles of engineering. You've simply been told that your reality is one of many possibilities. It feels like a philosophical sleight of hand. Furthermore, it invokes an infinite number of unobservable entities, the other universes, to explain the one we can see. Is this still science? A theory that makes itself immune to disproof by predicting every possible outcome is not by some definitions a scientific theory at all. If we can always fall back on the anthropic principle to explain away any feature of our universe, no matter how strange, then how can we ever truly test or falsify the multiverse hypothesis? This brings us to the final, formidable wall we must confront. If these other universes exist born from the eternal furnace of inflation, they are by their very nature causally disconnected from us. They are beyond our cosmic horizon, expanding away from us faster than light. No signal, no information, no light from them can ever reach us. They are sealed off forever beyond the realm of our telescopes and experiments. So how can we ever know if they are real? Are we deluding ourselves with a grand and beautiful mathematical story, a modern creation myth with no more connection to physical reality than the ancient tales of gods and titans? This is the front line of a fierce ongoing battle for the soul of physics. On one side are those who believe that a theory's power is not just in direct testable predictions, but also in its ability to solve pre-existing puzzles and its internal mathematical consistency. Eternal inflation, they argue, arises naturally from our best theories of the early universe. It elegantly solves the horizon and flatness problems. The multiverse is not an ad hoc addition, but an unavoidable consequence. The fact that it also explains fine-tuning is a powerful bonus. Science, they contend, must follow the logic of mathematics wherever it leads, even if that destination is beyond our observational reach. On the other side are the skeptics who hold fast to the traditional pillars of science, empirical evidence and falsifiability. To them, a theory of the unobservable is not a theory at all, but a branch of metaphysics. They warn that physics is losing its way, abandoning the hard-won discipline of experimental verification in favour of unfalsifiable aesthetic speculation. They fear that if we accept the multiverse, we open the floodgates to endless untestable stories that can explain anything and everything, ultimately eroding the credibility and authority of science itself. We stand at a crossroads peering into two futures for cosmology. In one, we embrace the multiverse as the ultimate paradigm shift, accepting that our reality is just a tiny fragment of a much larger unseen whole, and we learn to do science in a world without unique predictions guided by probabilities and anthropic reasoning. In the other, we pull back from the brink, rejecting the multiverse as a step too far into speculation, and continuing the search for a unique ultimate theory that can explain our universe, our laws and our existence without resorting to an infinity of others. The debate is fierce because the stakes could not be higher. It touches upon the very definition of scientific truth and the ultimate limits of human knowledge. The answers are not yet written. They are being forged right now in the fiery debates of conferences, in the dense equations on blackboards, and in the deepest recesses of human imagination. We have followed the chain of logic from a flicker of quantum uncertainty to the birth of our cosmos, and now to a vision of eternal creation. But this vision has left us grappling with infinities we cannot tame and realities we can never touch. The very theory that promised to explain our origins has led us to the edge of a philosophical abyss, forcing us to ask a terrifying question. Is the ultimate nature of reality fundamentally knowable, or have we finally reached the boundary where the map of science simply ends, and so we are left suspended contemplating a vision of reality so vast it threatens to dissolve our very sense of self? We've journeyed through the theoretical heart of eternal inflation, a cosmic engine of unending creation, where our entire observable universe is but a single crystallized bubble in an infinite effervescent sea of space-time. It is a staggering, perhaps unsettling proposition. A fractal cosmos of pocket universes, each born from a quantum leap, each potentially with its own unique laws of physics, its own destiny. But after such a breathtaking flight of imagination, we must inevitably return to Earth, grounded by one of science's most uncompromising questions. How could we ever know? How do you prove the existence of universes you can never visit? Worlds you can never see, realities forever walled off from us by an expanding gulf of inflating space-time. The very nature of the eternal inflation hypothesis seems to place its most profound predictions beyond the reach of any conceivable experiment. It feels at first glance like an untestable fantasy, a grand narrative belonging more to philosophy or mythology than to the rigorous evidence-based domain of cosmology. Yet to dismiss it so quickly would be to underestimate the relentless ingenuity of the human mind. For cosmologists, the impossible is not a barrier, it is a challenge. They know they cannot send a probe into another universe. They cannot peer through a telescope and watch another Big Bang ignite. But they suspect that if our universe was indeed born from such a chaotic, crowded cosmic foam, it might not have emerged entirely unscathed. Like a ship bearing the faint scars of a tumultuous voyage, our cosmos may carry subtle imperfections, ancient wounds from its violent birth. The trick is knowing where to look for them, and to find these primordial clues we must turn our gaze not outward to the space between galaxies, but backward in time, all the way back to the very first light. We must interrogate the most ancient artifact in our possession, the cosmic microwave background. This CMB, as we have seen, is the afterglow of our own Big Bang, a faint pervasive hum of radiation that fills the entire sky. It is a baby picture of our universe taken when it was just 380,000 years old. Before this moment, the cosmos was a searing, opaque plasma, a chaotic soup, where light was trapped endlessly bouncing between charged particles. But as the universe expanded and cooled, atoms formed, and for the first time light was set free to travel unimpeded across space-time. That liberated light stretched over 13.8 billion years into the microwave spectrum by cosmic expansion is what we see today. It is astonishingly, almost perfectly uniform in every direction you look. The temperature of this ancient light varies by only 1 part in 100,000. And yet within that whisper-faint variation lies the entire story of cosmic structure. These minuscule hot and cold spots are the seeds of everything we see today, the faint density fluctuations amplified by gravity over billions of years that grew into every galaxy, every star, and ultimately into us. For decades, our standard cosmological model has been incredibly successful at explaining the statistical pattern of these spots. The model, based on a single brief period of inflation that ended everywhere, predicts the size and distribution of these fluctuations with stunning accuracy. It is one of the great triumphs of modern science. But if eternal inflation is the true story, if our bubble is just one among many, then this pristine photograph might contain more than just the seeds of our own evolution. It might also contain evidence of an encounter. We're searching for a cosmic crime scene, and the CMB is the only witness. The prime suspect, a collision with another bubble universe. Imagine the scene in that primordial inflating ocean. Our bubble nucleates its walls of space-time rushing outward, its interior energy dropping to form the universe we know. But nearby in that same churning sea, another bubble does the same. As they both expand at the speed of light, their outer walls could theoretically collide. This would not be an explosion in the conventional sense. It would be a collision of two distinct realities, two separate domains of space-time grinding against each other. The encounter would send a cataclysmic shockwave of energy, a violent ripple in the fabric of space-time propagating into the hot, dense plasma of our infant universe. This wave would not be like anything we know. It would be a pure distortion of space itself, compressing and rarefying the primordial soup in its path, briefly altering the fundamental state of our cosmos in the region it touched. While the direct aftermath of such a collision would be long gone, its ghost might remain. That powerful shockwave racing through our early universe would have left a lasting impression on the very plasma from which the CMB was later released. It would have created a disturbance, a localized anomaly in the temperature of the radiation. It would have left, for want of a better word, a bruise. Searching for such a bruise on the cosmic microwave background is one of the most tantalizing high-stakes endeavors in all of science. Theoretical physicists have painstakingly modeled what such a signature might look like. A collision with another bubble would create a disturbance on its edge, and because of the geometry of the impact and our vantage point from within, that disturbance would appear projected onto our sky as a circular feature. Specifically, it would manifest as a distinct circular spot on the CMB, either hotter or colder than its surroundings, with a subtle but specific temperature profile across its disk. Critically, the statistical properties of the fluctuations inside this disk would be different from the fluctuations outside it. It would be an outlier, an aberration, a feature that our standard model of a single isolated universe simply cannot explain. Finding such a circular mark, a single anomalous disk standing out from the random mottling of the CMB, would be the closest thing we could ever have to a photograph of another universe. It would be the smoking gun of the multiverse. Spurred by this incredible possibility, teams of cosmologists have been meticulously scanning the CMB data, particularly the high-precision maps generated by the Planck Space Telescope. They employ sophisticated algorithms to hunt for these specific circular patterns, sifting through a sky of nearly random noise for one telltale sign of a cosmic fender bender. The search is excruciatingly difficult. Our own galaxy emits microwave radiation that contaminates the signal, acting as a foreground haze that must be carefully subtracted. And the CMB itself is naturally splotchy. It is entirely possible for random chance to create patterns that mimic the appearance of a collision disk. Differentiating a true signal from a statistical fluke is a monumental task, pushing the limits of our data analysis capabilities. To date, several intriguing candidates have been flagged circular features that seem to stand out. But upon closer inspection, none has risen to the level of a definitive discovery. The statistical significance has always been too low, the possibility that it is merely a random alignment of hot and cold spots too high. The jury is still out. The sky has not yet surrendered its deepest secret. But direct collisions are not the only potential clue. The eternal inflation framework suggests that our bubble universe may not be entirely alone, even if it hasn't collided with another. If the greater inflating metaverse is real, then the space beyond our observable horizon is not empty, but is instead a dynamic, energetic medium in which new universes are constantly being born. This vast overarching structure could exert a subtle gravitational influence on our own cosmic patch. The immense sea of inflating space-time outside our bubble, along with the gravitational pull of countless other distant bubble universes, could gently tug on our own, inducing a slight large-scale asymmetry or a preferred direction in the cosmos. In the simplest model of inflation, the universe should be isotropic, statistically the same in all directions. Yet some analyses of the CMB data have hinted at strange large-scale anomalies that defy this expectation. One of the most famous is the so-called axis of evil, a controversial finding from the WMAP satellite mission, later partially confirmed by Planck. This refers to an unexpected alignment of the largest features, the very biggest hot and cold spots in the cosmic microwave background. These features appear to be oddly correlated with each other, and even more bizarrely with the plane of our own solar system. Most cosmologists believe this alignment is a statistical fluke, a cosmic coincidence, or perhaps an unaccounted for error in processing the galactic foreground. Yet it stubbornly persists in the data. Some theorists have speculatively proposed that it could be the signature of a large-scale anisotropy, a slight stretching or shearing of our universe caused by the influence of the greater multiverse structure in which we are embedded. Another enduring puzzle is the CMB cold spot, a region of the sky that is anomalously large and anomalously cold far beyond what random fluctuation should produce. For years it was held up as a potential bubble collision candidate. The leading mundane explanation is that the spot is an illusion caused by a supervoid, an immense region of space between us and the CMB that is unusually empty of galaxies. Such a void would have a subtle gravitational effect on light passing through it, making it appear colder. While there is some evidence for such a void, it doesn't appear to be empty enough to fully account for the coldness we observe. The mystery of the cold spot, like the axis of evil, remains an open, tantalizing question mark on our map of the early universe. These are not proofs of the multiverse, but they are whispers. They are persistent anomalies, loose threads in our otherwise beautifully woven cosmological tapestry, hinting that the story might be grander and stranger than we ever imagined. While astronomers scan the heavens for these faint circumstantial clues, theoretical physicists have been uncovering a different kind of evidence, not from observation, but from the very foundations of fundamental physics. An extraordinary convergence has emerged from an entirely separate field of inquiry: string theory. For decades, string theory has been the leading candidate for a theory of everything, a unified mathematical framework that seeks to merge general relativity, the science of the very large, with quantum mechanics, the science of the very small. Its core idea is that the fundamental constituents of reality are not point-like particles, but unimaginably tiny, vibrating strings of energy. The different ways a string can vibrate correspond to the different particles we see, like electrons, photons, and quarks. For the theory to be mathematically consistent, however, it requires the existence of extra spatial dimensions beyond the three we experience. These dimensions are thought to be curled up, or compactified, into complex microscopic shapes known as Calabi-Yau manifolds. Here is where the connection becomes truly profound. It turns out there is not just one way to curl up these extra dimensions. The equations of string theory allow for a colossal number of different possible configurations, a breathtaking variety of stable Calabi-Yau shapes. Each one of these possible geometric solutions corresponds to a different vacuum state, a different ground-level energy for spacetime itself, and each distinct vacuum state would give rise to a universe with its own unique set of physical laws. The strength of gravity, the mass of an electron, the charge of a quark, the number of large spatial dimensions, all of these fundamental constants of nature are not uniquely fixed by the theory. Instead, they depend on the specific geometry of the compactified extra dimensions. String theory doesn't predict one single universe. It predicts a vast, sprawling landscape of possible universes. The numbers are staggering. Current estimates suggest there could be at least 10 to the power of 500 different stable vacuum states allowed by the theory. That is a 1 followed by 500 zeros. For years, this immense landscape was seen as a potential weakness of string theory. How could a theory be predictive if it allowed for an almost infinite number of outcomes? It felt like a failure. But with the advent of eternal inflation, this seeming flaw was transformed into a stunning virtue. Suddenly there was a perfect marriage between two of physics' most audacious ideas. Eternal inflation provided the dynamic engine, the mechanism for actually creating an endless number of universes, and the string theory landscape provided the blueprints, the vast menu of possible physical laws that those universes could adopt. The two theories complemented each other perfectly. The eternal sea of inflating space-time acts as a grand explorer canvassing the string theory landscape. As quantum fluctuations randomly jostle the inflaton field, they can kick small regions of space from one vacuum state to another. When a region lands in one of the 10 to the 500 stable valleys in the landscape, inflation ends, and a new bubble universe is born, crystallizing with that valley's specific set of physical laws. In this combined picture, our universe exists with its particular life-friendly parameters, not because they are the only ones possible, but because our bubble just happened to land in a valley of the landscape that produced them. In other valleys, countless other universes would exist with radically different physics. Some might have a much stronger force of gravity, causing them to collapse back into a singularity moments after their birth. Others might lack the electromagnetic force preventing atoms from ever forming. Still others might be bizarre higher dimensional worlds completely alien to our imagination. This synergy between eternal inflation and string theory provides a powerful theoretical underpinning for the multiverse. It takes the concept from a mere possibility allowed by one theory and elevates it to a natural, almost inevitable consequence of the union of our two deepest attempts to understand reality. It suggests that the vast diversity of potential worlds predicted by our most advanced mathematics isn't just a theoretical curiosity. It's a diversity that is actively being realized moment by moment within the churning cosmic ocean. And so the search continues on two parallel fronts. On one side, the observers, the cosmic cartographers, meticulously sifting through the faint light of creation, hunting for a definitive crack in the porcelain perfection of our standard model. They search for the bruise, the asymmetry, the telltale scar that betrays a history more violent and more crowded than we ever suspected. On the other side, the theorists, the architects of reality, delve deeper into the labyrinthine mathematics of string theory, exploring the contours of the landscape and refining their predictions for what signatures we might find. Both are reaching for the same thing, a glimpse of what lies beyond the horizon, a confirmation that our cosmic shore is not the only one. Right now, the evidence remains tantalizingly out of reach, a collection of whispers, anomalies, and compelling theoretical arguments. We have a motive and a suspect, but the case is not yet closed. We are left standing at a profound crossroads in our quest for understanding, and this uncertainty forces us to confront an even deeper, more unsettling set of questions. Questions that push beyond the boundaries of physics and into the realm of philosophy itself. If our universe is just one of many a lucky draw in a cosmic lottery of incomprehensible scale, then what does that mean for our own existence? What does it say about our place and our purpose in this seemingly infinite cosmic tapestry? And so, we arrive at the precipice of our cosmic voyage, looking out not upon a silent finite darkness, but upon an endlessly turbulent ocean of creation. We began with a single question, a query that once seemed to border on the metaphysical: is the Big Bang still happening elsewhere? After journeying through the quantum realm, across the unfathomable energies of the first moments, and into the vast theoretical landscapes of modern physics, the answer that emerges is not a hesitant whisper, but a resounding revolutionary affirmation. Yes, in the grand tapestry woven by eternal inflation, the genesis of our universe was not a singular, unrepeatable miracle. It was and is merely one event, one flash of light in an eternal furnace of cosmic birth. The Big Bang, our Big Bang is over for us. But the process that ignited it, that magnificent inflationary engine, has never truly stopped. Somewhere unimaginably far from our own cosmic shores, beyond the reach of any conceivable telescope, a new universe is right now bursting into existence. And another, an infinite, unending cascade of creation. This realization represents more than just a new chapter in the textbook of cosmology. It is a fundamental demolition and reconstruction of our entire cosmic address. For millennia, we have gradually and often reluctantly accepted our demotion from the center of existence. We learned the Earth was not the heart of the solar system, that our sun was just one star among billions in an average galaxy, and that our galaxy was a single mote of dust in a colossal cosmic web. Each step was a lesson in humility. But eternal inflation proposes the ultimate dethronement. It suggests that our entire universe, all the 100 billion galaxies stretching across 93 billion light-years of observable space, everything we have ever known or could ever hope to see, is but one bubble in an infinite cosmic foam. We are not just on a pale blue dot in a vast emptiness. We are inhabitants of a single, perhaps unremarkable island in an infinite archipelago of realities, each with its own potential set of physical laws, dimensions, and destinies. This shift from a universe to a multiverse is the most profound paradigm change humanity has ever been asked to contemplate. It forces us to redefine what everything even means. The familiar night sky, the celestial map that has guided our ancestors and inspired our poets, becomes a local phenomenon, the view from a single window in an infinite mansion. The laws of physics we have painstakingly uncovered, from gravity to quantum mechanics, those seemingly universal and immutable truths, may not be fundamental edicts for all of existence, Instead, they might be the local bylaws of our particular cosmic bubble emergent properties settled upon as our pocket universe cooled and expanded. In other bubbles, the strength of the electromagnetic force could be different, rendering chemistry impossible. The number of spatial dimensions might be 4 or 10 or 26. The very particles that constitute matter could be entirely alien. We have moved from believing we were studying the blueprint of reality to realizing we might only be studying the architecture of our own room. But is this magnificent, almost terrifying vision merely a beautiful piece of mathematics, a philosophical indulgence born from abstract equations? Or can we find a way to test it to hear the echoes of these other creations? The search for evidence is one of the most exciting and challenging frontiers in all of science. It pushes our ingenuity to its absolute limits. Cosmologists are meticulously scanning the cosmic microwave background radiation, that precious first photograph of our own universe, for any telltale signs of a cosmic collision. They hunt for a specific kind of bruise, a circular cold or hot spot in the ancient light, which could be the scar left by a violent encounter with another bubble universe in the distant past. Such a discovery would be the single greatest observational triumph in history, transforming the multiverse from a theoretical possibility into a physical reality. It would be like finding the footprint of another person on a supposedly deserted island. The quest also extends into the unseen realm of gravitational waves. The theory predicts that the violent birth of our universe and the endless churning of the inflationary sea should have generated a unique background of these ripples in space-time. Detecting this primordial gravitational wave signature would be like hearing the faint lingering rumble of creation itself, providing powerful corroboration for the inflationary model that underpins the entire multiverse concept. Projects on the ground and planned for space are being designed with ever-increasing sensitivity, straining to catch these whispers from the first trillionth of a second. This is not a passive search. It is an active, ongoing investigation. Physicists are not content to let the multiverse remain a story. They are building the tools to interrogate reality at its most fundamental level, determined to find a crack in the wall of our cosmic isolation. At the same time, theoretical physicists continue their own explorations, venturing deeper into the mathematical framework of string theory and M theory. Within these elegant but labyrinthine structures, they have discovered what they call the landscape of theoretical space, with an astronomical number of possible solutions, perhaps 10 to the power of 500 or more. Each solution corresponds to a different vacuum state, a different way a universe could be. Eternal inflation provides the dynamic mechanism to populate this landscape, to turn these mathematical possibilities into physical actualities. The synergy between these two fields is powerful. String theory provides the what, the vast menu of possible universes, while eternal inflation provides the how, the cosmic engine that manufactures them without end. Though we are far from a final unified theory, the convergence of these independent lines of inquiry suggests that we are on a path toward a deeper and more complete understanding of reality's foundations. And as we walk this path, we are confronted with profound philosophical questions that resonate far beyond the laboratory or the observatory. If there are infinite universes, then the anthropic principle, the observation that our universe appears finely tuned for life, finds a natural and startlingly simple explanation. We find ourselves in this particular bubble, with its specific set of life-permitting laws, for the same reason we find ourselves on Earth rather than Jupiter, or the surface of the Sun. We are here because this is one of the rare places where we could be. There is no grand cosmic miracle in our existence, no evidence of a fine-tuner. Instead, our existence is a matter of statistics, a selection effect. We are the inevitable outcome of an infinite cosmic lottery. In a multiverse, anything that is not forbidden by the fundamental laws of physics is compulsory. Everything that can happen will happen an infinite number of times. Think for a moment about the sheer weight of that implication. It means that somewhere in a universe causally disconnected from our own is a world almost identical to ours, but where you made a different choice this morning. And another where a key moment in history played out differently. And another where the evolutionary path of life on Earth took a wildly different turn. It suggests a reality where every quantum probability, every fork in the road is realized in some corner of the multiverse. This is not science fiction. It is the logical philosophical endpoint of the theory of eternal inflation. It challenges our notions of identity, of uniqueness, of the significance of our choices. Are our lives merely one narrative thread in an infinite library of all possible stories? This concept is as exhilarating as it is unsettling, forcing a re-evaluation of our place not just in the cosmos, but in the totality of all that is, was, and ever could be. This new cosmic paradigm also reshapes our understanding of beginnings and endings. The idea of a single definitive creation event, our Big Bang, is replaced by a process of eternal genesis. The multiverse as a whole has no beginning, and in all likelihood no end. It is a self-perpetuating, self-creating system. It simply is. Our universe had a beginning and will one day face its own end, whether through heat, death, a big crunch, or a big rip. But we are a temporary chapter in an eternal book. The story of existence itself will continue. Creation is not a historical event. It is a continuous, ongoing process. This perspective offers a kind of cosmic immortality, a reassurance that even if our own light fades, the creative impulse of reality will persist endlessly, generating new worlds, new possibilities, and new wonders. So where does this leave us? We stand on a tiny world orbiting an average star in a quiet suburb of a vast galaxy, which is itself just one island universe in a possibly infinite sea of others. This knowledge could be seen as terrifying as the ultimate statement of our own insignificance. If our entire cosmos is just a bubble, what meaning can our tiny lives possibly hold? But there is another way to see it, a perspective not of despair, but of profound inspiration. The same science that reveals this unimaginable scale also reveals that we are a part of it. The atoms in our bodies were forged in the hearts of stars that exploded billions of years ago. The consciousness with which we ponder these questions is, as far as we know, one of the most complex phenomena our universe has ever produced. We are not separate from this cosmic grandeur. We are a manifestation of it. We are the universe becoming aware of itself. In a potentially infinite multiverse, the fact that we are here now, in this particular configuration of matter and energy, able to ask these questions, is what truly matters. Our significance is not derived from being at the centre of existence, but from our capacity to understand our place within it. We are the sentient edge of this particular bubble, the part of the cosmos that can look back and piece together the story of its own origins. This is a privilege of immense proportions. Our quest for knowledge, our art, our music, our love, these are the things that give meaning to our corner of reality. They are not diminished by the existence of other worlds. They are made all the more precious because they are our unique expression of the cosmic potential. The journey to understand eternal inflation is in the end a journey into the heart of what it means to be human. It is driven by that same innate curiosity that led our ancestors to first look up at the stars and wonder. It demands a humility that accepts our true cosmic place, but also a boldness to imagine realities far beyond our own experience. It reminds us that science is not just a collection of facts, but a deeply human story of discovery, a relentless effort to push back the darkness and replace mystery with understanding. And with every new discovery, we find that the universe is not simpler than we imagined, but more complex, more bizarre, and more magnificent than we ever dared to dream. We may never see these other universes. We may never receive a signal from another cosmic bubble. Their existence may forever remain on the other side of a theoretical horizon, testable only through the faintest, most subtle clues left behind in our own cosmic backyard. But knowing that they are likely there changes everything. It fills the cosmos with a sense of boundless potential. It transforms the cold, empty voids between galaxies into the space between islands of creation. It tells us that the magnificent, awe-inspiring universe we see is just the beginning of the story. The Big Bang is not just our distant past. It is the perpetual, eternal future of a reality that is constantly, gloriously renewing itself. And we, for this fleeting moment, have the extraordinary privilege to bear witness.